my PU2 aspirants, so your midterm exams are ahead, and in this video we are going to do one short revision of the chapter coordination compounds. Okay, so this is going to be a super easy chapter. You just need to know some basics and then you can kill this chapter. Okay, so let's see about what is the blueprint of this chapter. So you will be getting one marker question. There will be two questions, one marker. Okay, it can be either in MCQ form or in the form of FIB or fill in the blanks. Next, there is a section B where you get two marker questions, right? So there will be one question in that from inorganic chemistry. That one question from inorganic chemistry can either be from coordination compounds or from the DNF block chapter. So you may get a two marker question here also. Then comes section C where there is three marker questions, right? In section C we have in section C you have I think question number 4 and question number 5. Okay, so in question number 4 you will get inorganic questions. There will be 5 questions, so it will be 3 plus 2, means either 3 from coordination and 2 from DNF block, or the ulta, like DNF block will have 3 questions and coordination will have 2 questions. So you can either get 2 or 3 questions in the 3 marker section. Okay, so total weightage of this chapter is 10. Clear? So you can have 2 mark here, 2 mark here, and if you are getting 2 3 marker questions here, then here it will be 6. Okay, or you can have 2 here, and if you are getting 3 marker 9. Okay, this may change to 1. So you may get 1 to 2. The total weightage will be 10. It will be distributed in this way. So now let's move to the topics that we have in this chapter. So first we will talk about Werner's theory. Definitely many of the times the postulates of Werner's theories are directly asked in the exam. Next, some important definitions. This can also be asked in the 2 marker question very easily. Nomenclature, very important topic. Isomerism, very important topic. Bonding theories, metal carbonyls, and applications. Okay, 7 topics are there for discussion. Let's start one by one. So first let's talk about basically what is a coordination compound. So we have 3 types of bond. One is ionic bond, one is covalent bond, and another is a coordinate bond. So what do you mean by a coordinate bond? So when there is a bond, and if you remember, every bond has 2 electrons, right? If A and B are forming one bond, A donates 1 electron, B donates 1 electron, and then we get AB bond, right? But there is also a possibility that both the electrons are donated by a single element, means you have like this, and both these electrons are donated by this single element. Okay, so in that case that is called as a coordinate bond. Okay, this is called as a coordinate bond. So when in the elements, one element donate both the electrons to form a bond, that is called as a coordinate bond. Okay, now in this chapter, what will be our metal? Metal will be mostly our transition metals. Okay, so our metals will be transition metals, and we will have the one which is donating electrons. We will call them as ligands. Okay, and ligands will donate electrons to the metals to form a coordinate bond. I hope this is clear. Now let's see. So what can be ligands? Ligands can either be neutral or negatively charged molecules. Okay, moving forward here to first topic, that is Werner's theory. So now what does Werner's theory says about the metal ligand bond and this complex compounds? Okay, so Werner's has given us 2 statements that every coordination compound has 2 valencies, primary valency and secondary valency. Okay, this is the introduction point. Next, you have to write the 2 valencies. What are the postulates? The primary valencies are normally ionizable and are satisfied by negative ions. Okay, so if you see, there is a complex looks like this. You have something inside the square bracket and you have something outside, or you can have outside something and then square bracket. Okay, so there is, here we have metal and ligand, and here we have metal and ligand. Okay, so the primary valencies are normally ionizable and satisfied by negative ions. So the valency of this particular complex, okay, the valency of this particular complex is called as the primary valency. Okay, and the secondary valencies are non-ionizable and satisfied by neutral molecules or negative ions. Now this metal will have a charge, okay, or we call it as the oxidation number, the oxidation number of the metal. Okay, so the secondary valency is also the coordination number of the metal. Now what is the coordination number? Coordination number is how many metal ligand bond is formed. That is called the coordination number. Okay, so if a metal is forming 4 bonds with the ligand, then the coordination number is 4. So that coordination number is your secondary valency, and this oxidation number of the metal is your primary valency. Okay. Next, the ions or groups bound by the secondary linkages to the metal have characteristic spatial arrangements corresponding to different coordination numbers. So based on this metal ligand bond, we have different types of geometries. So if there are 4 ligands bounded, there will be a specific shape. If there are 6 ligands bounded, there will be a specific shape. If there are 2 ligands bounded, it will have a specific geometry. So the metal ligand bond here, how many ligands are bonded to the metal, decides, or the secondary valency decides the geometry of the molecule. Okay, so what are the postulates we have? The first postulate is every coordination compound has 2 types of valency, primary valency and secondary valency. Now what is primary valency? It is ionizable and satisfied by negative ions. What is secondary valency? It is non-ionizable and satisfied by neutral and negative ligands. And the secondary valence is also equal to the coordination number of the metal. Okay, now what is coordination number? The number of bonds that is formed by the metal with the ligand. And this secondary valency also decides the spatial arrangement, or also can we say that the geometry of the molecule is also decided by this secondary valency. Okay. Now here a question can also be asked about the difference between primary and secondary valency. So from here you have to just find out the difference between. Now moving to the next one, important definition. So here we have 6 topics on which you should know the definition. Coordination entity, central atom, ligand, coordination number, oxidation number, and homoleptic and heteroleptic complexes. So I'll be telling you each and everything from where questions can be asked, which definitions you have to remember, we'll discuss. Okay, so first let's talk about this image. Okay, now you can see this whole thing. Okay, this one, this square bracket, whatever is present inside this whole thing, this is called as coordination sphere. Okay, this whole thing is called as coordination sphere. Whatever is present in the square bracket and inside it, the whole thing is called as coordination sphere or entity. Okay. Now what I have here, in this coordination sphere, there is a metal atom and there is a ligand. There will be one metal atom and there will be different ligands binding to that. So this central metal is called as central atom, and the ligands that are binding here is called as, or the ions which are forming bond with the metals are called as ligands here. Next we have this, how many ligands are binding to this one, that is your coordination number. As we have told you, this is the number of metal to ligand bond that has formed. This is called as coordination number, and we also called it as secondary valency. Just now I have discussed, right? Next what we have, the other ion which is present outside this square bracket. It can either be on this side or it can be this side. These are called as counter ion or auxiliary ion. Okay, so this is the entire things of the coordination sphere, metal, ligand. So that is what you should be knowing. Now we will know more about ligands. So we have these definitions about ligand. We have to know about what is the denticity of a ligand, what is an ambidentate ligand, and what is a chelating ligand. Okay, so let's see. Okay, denticity, just a minute. So how will I define density? Denticity is the number of bonds, okay, number of bonds formed by a ligand with metal. Okay, so if a ligand is there and a metal is there, a ligand can form only one bond with the metal, then it is called as monodentate ligand, okay, or unidentate ligand. If a ligand can form one single ligand, it is having two donor sites and it can form two bonds with the ligand, then it is called didentate or bidentate ligand. Similarly, if a ligand has four donor sites, we call it as a tetradentate ligand. So we have generally monodentate or unidentate, bidentate, tetradentate and hexadentate ligands we have studied. Okay, so I'll show you some denticity definition. So you can see this particular ligand, okay, this is called as EDTA. Okay, ethylene diamine tetraacetate. So you can see how many donor sites are there. Suppose a metal is there, okay, suppose a metal is there, so how many bonds it can form, do you know? Here this is a donor site, 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 then we have this also a donor site and this also a donor site. So from this one particular ligand there can be 6 donor sites, or this one particular ligand forms 6 bonds with the metal. So the coordination number of the metal is 6 because it is forming 6 bonds, but this one single ligand, it can be called as a hexadentate ligand because it is having 6 donor sites. Okay, I'll give you some more example. So for example, if I have one more ligand is there, that is ethylene diamine. Okay, and you have a metal here. So now what happens, the lone pair of this one form bonds here. Okay, lone pair of this one form bonds here. So you can see that there are 2 donor sites from this ligand. This one particular ligand form 2 bonds with the metal, right? So when it forms 2 bonds, that means what? It is a bidentate ligand. Getting? So these type we have monodentate, bidentate, tetradentate and hexadentate. Monodentate, you can see normal if I have a metal and a Cl ligand is present, or if you have water ligand, or you have NH3 ligand. I'll draw like this, NH3 ligand. So these are all monodentate ligand because they are forming single bonds with the metals. Okay, now let's see next one, what is an ambidentate ligand. So you might have some confusion regarding a bidentate ligand and an ambidentate ligand. So please listen carefully the difference. Okay, so I'll tell you what. See, suppose this one, CH2, NH2, CH2, NH2, and I have a metal. So this N forms bond, this M forms, so this is a bidentate ligand. Now there can be also an ambidentate ligand. So I have Cn, okay, Cn can form bond with metal, or Nc can form bond with the metal. Okay, so what I'm saying, see, in ambidentate ligand also there are 2 donor sites. C can also form bond, N can also form bond with the metal. There are 2 donor sites, but only one will form bond with the metal at a single time. Means both of them are not forming bond at the same time with metal. When C forms, N is not forming. When N forms, C is not forming. But there are 2 donor sites. So a ligand which has 2 donor sites, but only one can form bond with the metal at a single time. Those type of ligands are called as ambidentate ligands. Getting? I hope all of you are getting this one. If you are getting, please put down in the comment section that you have understood. Now bidentate ligand is also having 2 donor sites, but both the donor sites form bond with the metal at the same time. Okay, you can see NH2 and NH2 both are forming bond with the metal at the same time. Okay, there are many examples of ambidentate ligand. So you have also NO2 a ligand. It is like this. So O forms bond here, metal, and then you have N also like this. N can also form bond with metal. Okay, so you can see O is a site and N is also a site. So both of them are donating to the metal, but at different cases. Okay, so when Cn donates, we call this cyanido. This ligand is called as cyanido, and if Nc is formed, then we call it isocyanido. Okay, so the name becomes different. I hope you are getting what is a ambidentate ligand and what is a bidentate ligand? So you can see NO2, N is forming bond and O is forming bond. So when N is forming bond, this ligand is called as nitrito N. When O is forming bond, we call this ligand as nitrito O. Similarly, when SCN and NCS is also there, when S is forming bond, we call it thiocyanate S, and when N is forming bond with the metal, we call it as thiocyanate N. Okay. Moving forward, the next thing is homoleptic and heteroleptic complex. This is very simple. So if a metal form bonds with the same type of ligands or same ligands, then we call it as a homoleptic ligands. So you can see here cobalt forms bond with 6 NH3 ligands. All the ligands are same. All the 6 ligands are ammonia. So this type of complex is called as homoleptic. Okay. Now what is heteroleptic ligands? So heteroleptic ligands means where we have different types of ligands. So you can see here we have 4 ammonia and 2 chlorine ligands are there. These are different ligands. So that is why what will happen? We will have heteroleptic ligands. Okay. Now moving forward to nomenclature. So first of all, we'll see how to name this coordination compounds. Okay, there's a certain rules that you need to follow. So the first rule is every time when you see a cation should be named first and then the anion. So there are 2 possibilities. You can have like this or you can have like this. So in this is auxiliary ion, okay, and this is the complex. And here this is the auxiliary ion and this is the complex, right? The one which is written first is the cation, the one which is written in the second is always anion. So this is cation, okay, and this is anion. Similarly here this is anion, sorry, this first one is cation and this one is anion. Okay, so always the first one is written. So when you name it, the first thing you have to name is cation and the second thing you have to name is anion. Okay, that's the first rule. Next is when you name the complex. Now coming to when I naming this complex, inside this complex what I have? Metal and ligand. Here also I have metal and ligand. So whenever you are naming the complex, first you have to tell the ligands, name of all the ligands present, and lastly comes the name of the metal. And these ligands should be written in alphabetical order. Okay, if there are more ligands, then you have to follow alphabetical order and then you have to write the name of the ligands and then you have to write the name of the metal. Okay, so first rule is clear. First we have to write the cation name and then the anion name. Now whenever I am writing the complex name, whether it is in the cation form or in the anion form doesn't matter, but whenever you are writing this complex, always the ligands should be written first in alphabetical order followed by the name of the metal. Okay, next we have rule, the name of the anionic ligand. So ligands will be generally negatively charged or neutral atoms, right? So if the ligands are negatively charged, there the name should end with O. So for example, if you have one second, let me give some example. For example, if you have chlorine ligand, okay, you name it as chlorido or chloro. You can tell it chloro or chlorido. Okay, for example, you have Cn minus. We call it as cyano or cyanido. Okay, so you are seeing it should end with O. Okay, and those of the neutral and cationic ligands. So generally we don't have cationic ligands, but there might be some cationic ligands, but those who are neutral, there are some exceptional name for that. So we use for water, we use the word aqua. Okay, then for ammonia we use the word amine, and for CO we use the word carbonyl, and nitrosyl for the word NO. Okay, so for these are the NO is a positive ligand, NO plus is there. Okay, other these 3 are neutral ligands. So for neutral ligands we have a different name, but for negative ligands we have the name should end with O. The ligand name should end with O. Okay. Moving forward to the next one. So now if there are more than one ligand, so for example you have 4 ammonia present in a 2 chlorines are present, something like that, then prefixes like mono, di and tri are used to indicate the number of individual ligands in the coordination entity. I'll give you example, we'll solve some questions, you'll be clear. So here what you have to do is basically these numbers indicate the number of ligands present. Okay. When the names of the ligand include a numerical prefix, then the term bis, tris, tetrakis are used, the ligand to which they refer being placed in the parenthesis. Okay, so there are certain ligands for which we have to use word like bis, tris and tetrakis to denote the number of ligands. So where we can use, so basically with ethylene 1,2-diamine, this is the ligand. Okay, here we use this letter bis, tris or tetrakis. Okay, next, after oxidation, when you write the complex name, okay, complex name, what it is, followed by ligand name in alphabetical order, then metal name, and after the metal name the oxidation state of the metal is written, okay, and in Roman numbers it is written in parenthesis. Okay, I will give you example, it will be more clear. Next, if the complex ion is a cation, the metal is named as same, but if the complex ion is an anion, then the metal ends with a suffix ate. Okay, so we have a complex ion, okay, and if you have metal and ligand. Now if this complex ion is cation, so how will you name it? First you have to write the name of the ligands, okay, then you have to write the name of the metal, and then you have to write the oxidation state of the metal in Roman number. Okay, and if you have this metal, ligand, and you have this -1, so here if this is an anionic complex, you have to write the ligand's name, then you have to write the metal's name. Okay, this metal name should end with ate. Okay, this metal name should end with ate, and after that it should be having this, that is the Roman number. You have to write the oxidation state of the metal in Roman number. Clear? Okay, now let's move forward. So here are some examples of the ligands and their names that you should remember. So fluorine is fluorido, chlorine is chlorido, bromine is bromido, iodine is iodido, sulfate is sulfato, OH is hydroxo, CN is cyanido, C2O4 is oxalato, CO3 2- is carbonato, O2- is oxo, O2 2- is peroxo, O2- is superoxo. Then these all are not that much in use. NO+ you should just remember nitrosonium. And neutral ligands, we have NH3 amine, H2O aqueous, CO carbonyl, NO is nitrosyl, O2 dioxygen, N2 dinitrogen, and this is ethylene 1,2-ethylene diamine. Okay, next we'll solve some questions here on how to write the name of the compounds. So you can see, suppose this compound I want to write. Okay, so first of all what I have to write, you can see that there is no cation anion, it is a neutral complex. Okay, so neutral complex is there. So first let's write the name of the ligands. So this ligand name is amine, this is chlorido, this is nitrito N, right? So now if I want to write the name, first I will start with amine alphabetical order. So diamine. Okay, next I have chlorido, or you can write chloro also, diamine chloro, nitrito N. If it is written ONO, then it is nitrito O. If it is NO2, means N is forming bond, it is an ambidentate ligand, so nitrito N. After that I will write the name of the ligand, metal, that is platinum. Okay, now here I have to write the oxidation state of the metal in Roman number. So let this be X. NH3 is a neutral ligand, chlorine is -1, NO2 is also -1, right? So what is the oxidation state of this one? It is, so I can write X plus 0 -1 -1. The total charge of the complex is also 0, so that is by 0. So I'll get +2, so it will be written in this way. Okay, now let's see this one. You have potassium first. Okay, so first the cation part should be written, which is potassium. So let's write here potassium. Okay, next the ligand, here is only one ligand, C2O4. So what is C2O4 ligand? If you see, have I given you that? Yeah, C2O4 is oxalato. How many it is there? 3 is there, right? So I have tri-oxalato. Okay, next this is the anion, this is cation part, this is anion part. So in anion part what will happen? The name of the metal should end with ATE. So the name of the metal is chromium, so it will become chromate. Okay, lastly what I have to write? The oxidation state of the metal. So how can I write that? So the potassium is +1, there are 3 potassium, so plus 3, here it is plus 3. Chromium I have to find out, so it is X. C2O4, what is the charge of C2O4? Minus 2. There are 3 there, so 3 into minus 2, it will be minus 6 is equal to 0. So X will be plus 3, so it can be written like this. Okay, potassium trioxalatochromate 3. Clear? Now let's move to the next topic, that is isomerism. So isomerism, we have 2 types of isomerism, stereoisomerism and structural isomerism. Okay, so we'll see first of all, under stereoisomerism also we have 2 topics, geometrical isomerism and optical isomerism. Under structural isomerism, we have linkage isomerism, coordination isomerism, solvation isomerism and ionization isomerism. These are the 4 types of structural isomerism. Now in case of stereoisomerism, we have geometrical and optical. Now under geometrical, we'll study 2 coordination number 4 and coordination number 6. If I have coordination number 4, we have these type of structures possible, square planar and tetrahedral. In coordination number 6, there is only one structure possible, that is octahedral. Okay, and this octahedral means there will be 6, coordination number 6, we can have these all possibilities, that is Ma4B2, Ma2LL whole 2, Ma3B3. Now what is this? I'll explain, don't worry. Okay, let me just tell you this complete thing once again. Under isomerism, so first of all, what is isomerism? Isomerism means having same formula but different structures. Okay, what is isomerism? You must have known what is isomers. It is same formula but different structures. Now what is structural isomerism? Structural isomerism is same formula and different structures, but stereoisomerism is what? They have same formula, okay, same bonding but different spatial arrangements. Okay, means here the bonding will also be different in structural isomerism, but in stereoisomerism the metal ligand bonding will be same, but the arrangement in the space will be different. When example will be given, it will be more clear. Now stereoisomerism is again of 2 types. One is your geometrical isomerism and another is your optical isomerism. Geometrical isomerism we will study for 2 coordination numbers, that is coordination number 4 and coordination number 6. When a complex is having coordination number 4, what all structures it has possible? It can either be in the form of tetrahedral or in the form of square planar. Now when it is octahedral, when it is having 6 bonds, or when its coordination number is 6, how can we write it? We can write it as Ma4B2, Ma2LL whole 2 and Ma3B3. So I'll draw this and show you to understand. So if coordination number 6 is there, I can have first of all M, so you can have this one ML6, okay. Here there will be no isomerism because all the ligands are same, right? You cannot have any isomerism here. Now next we can have is Ma4B2, okay, means you have, there are 6 bonds, right? So you have A4, 4A are there and 2 B's are there. This is Ma4B2 type. There can be, we'll see what all isomers are possible, that there are 6 bonds like this. Now what is MLL whole 2 and B2? Now LL whole 2 means you have bidentate ligands, okay. This is L here bidentate, this is bidentate, okay, MLL, and then you have A2. Okay, next we have Ma3B3. Okay, so here also there will be means out of 6 ligands 3A is present and 3B is present. In MLL whole 2 A2 there are 2 bidentate ligands and there is 2 monodentate ligands. Okay, each bidentate ligand will form 2 bonds, so there is 2 bonds here. Another bidentate ligand will form another 2 bonds, so total 6 bonds should be forming here. Okay, so in coordination number 6 we have these all possibilities. Now let's look at the isomerism. So first geometrical isomerism for coordination number 4, square planar and tetrahedral. So in square planar, if you see, What is the formula for square planar? You have Ma2B2. Okay, Ma2B2. There will be 4 branches. So if both the two ligands, so if you consider this example PTNH3 whole 2Cl2, 2 NH3 groups are on the same side, okay, and 2 chlorine are on the same side. Next you have 2 NH3 on the opposite side and 2 chlorine on the opposite side. So when we have on the same side, we call it as cis isomer, and when we have it on the opposite side, we call it as trans isomer. Okay, so these are the 2 types of what I'll say geometrical isomerism for coordination number 4. Now coming to the next one, in tetrahedral structures do not show geometrical isomerism. Now what is tetrahedral structure? It is like M. If the structure is like this. What is square planar? Square planar is like this. All the 4 bonds are in one plane. That is called square planar. If you have a tetrahedral structure like this, okay, then there will be no geometrical isomerism possible. Now the reason for here, all the groups are equidistant, equally spaced in the spatial arrangement, so we cannot have any difference there. So no isomerism in tetrahedral structure. Now moving forward to coordination number 6. So I told you that there will be 3 possibilities in which we can write the coordination number 6. First is MX4L2. So here you can see, if I have this example CONH3 whole 4 Cl2. CONH3 whole 4 Cl2. So if these 4 NH3 ligands are in one plane, okay, you can see here 4 NH3 ligands are in one plane and the chlorine are on the tops or on the apex points. 2 chlorine are opposite to each other, then we call it as a trans isomer. Okay. Now if anything else is there, means the chlorine, means there is nothing which is directly opposite to each other. So you can see any other arrangement except than this one. You can see 3 NH3 in the plane, 2 chlorine are 1 chlorine in the plane, 1 is in the apex, 1 NH3 is here. So any other arrangement other than this will be called as cis isomer. Okay. Now coming to the next one, MLL whole 2 X2. Now here also if you see this particular arrangement where these chlorines are 2 opposite side, the En are opposite to each other, this is called as your trans isomer. Okay, and this one where you can see the chlorine are closer to each other and En are closer to each other, this is your cis isomer. Okay, next coming to this is your Ma3B3 type. This is MX3L3, Ma3B3 type. So here we have 2 types of geometry. So you can see the example of CONH3 whole 2 NO2 whole 3. Now when you have Ma3B3 type, we give a special name for that, not cis and trans. It is called facial or meridional. Okay, so if you have all the 3 NO2 on one side and 1 NH3 on, if you just draw a diagonal here, NH3 on one side and NO2 on one side, this is called facial. And if NO2 are present in one plane, all the 3 NO2 are present in one plane, we call it as meridional. Okay, facial and meridional isomers are existing for Ma3B3 type. Okay, now moving to the optical isomerism. Here you have to understand 2 types of compounds will show optical isomerism. For coordination number 6 we are talking. Okay, so for coordination number 6, if you have a structure like this, MLL whole 3, okay, this one will show optical isomerism, and there's one more possibility, that is MLL whole 2 A2. Okay, the cis form of this one will also show optical isomerism. Now let's see, this is COEN whole 3. Like this is, En is a bidentate ligand. Okay, this is a bidentate ligand. 1 bidentate ligand forms 2 bond, 3 will form 6 bonds. So it is a coordination number 6 compound. So if you have a structure like this, optical isomerism means what? There they have non-superimposable mirror images. Okay, they have non-superimposable mirror images. Okay, they have non-superimposable mirror images. So that is a part of this. Is, you can see, if I just draw the mirror image of this one, this is non-superimposable. So this is a kind of optical isomerism. And the cis form, if you have the cis form, if you transform, it will be superimposable. So that is why it is not optically active. So I'll just show you example. If I have this PT Cl2 En2, right? So if I just draw like this, if I draw its mirror image, means just the reflection of this one, so I'll get the compound like this. Right? So now this one is exactly superimposable on this one, and this is the transform. So when it is exactly superimposable on each other, they do not form optical isomers. So the condition for optical isomers is they should have non-superimposable mirror images on each other. Okay, so that is why transform will not have, but the cis form will work. So in optical isomerism, you need to check these two type of compounds. If they are following these formula, then definitely they will show optical isomerism. Okay. So with this, we have completed stereoisomerism. Let's see the structural isomerism. So structural isomerism is very easy. We have 4 types of structural isomerism. Linkage isomerism comes with ambidentate ligands. Okay, so you can see here example. So if you have CONH3(5)NO2Cl2, suppose this is a complex. Now here N is binding. Okay, just I can write another molecule like this. One second. So I can write another molecule like this, CONH3(5)ONO(Cl2), right? So here N was forming or linking, here O is linking. So these are 2 different compounds. So that is a type of linkage isomerism. Next we have coordinate isomerism. So here you can see CONH3(6) and CrCN6. CrCN6 is there. Now if I just cross change or exchange them, you will get COCN6 and CrNH3(6). Right. So here if you see there is an exchange of ligands between the coordinate pairs, we call it as coordinate isomerism. Now talking about ionization isomerism, so I'll just erase this one here. One second. Yeah. So this one will be like this, CONH3(5)ONO(Cl2), and this one I can write like this, COCN6CrNH3(6). We can have a change of ligands. Now what is ionization isomerism? Now see, when you put this one in dissolve in water, what ions you will get? This whole complex will be one ion and Br minus will be another ion. If I just exchange this one, if I put this one in water, we'll get this whole compound as one ion and SO4 as one separate ion. So the ions that is formed when you put this compounds in water, the ions that are formed are different. In that case, it is called as an ionization isomerism. Next, for solvation isomerism, we have CrH2O(5) Cl2.H2O. So here what happens, you can see the number of water molecules. Here we have total 3 water molecules, right? So now you can just arrange this in any way. You can take these water molecule inside, you can exchange in any way. So there are total 6 H2O molecules. I have taken all of them inside and I have taken chlorine outside. So it is very similar to ionization isomerism. You just need to include water molecule here. Okay, so examples you have to remember and definitions you have to study for these isomerisms. Now let's move to the part 3 of this chapter, that is bonding theories. Okay, so in bonding theories I have valence bond theory and crystal field theory, and under crystal field theory we have again octahedral and tetrahedral, and after that I'll be discussing about the color of the compounds, or why do coordination compounds have so bright colors. Okay, let's start the first one, that is your valence bond theory. So in valence bond theory what it says is, according to this theory, the metal atom, the metal atom or ion under the influence of ligands can use their N-1d and Ns or Np and Ns orbitals for hybridization to yield a set of equivalent orbitals of definite geometry such as octahedral, tetrahedral, or square planar. Basically what is it saying is the metals orbitals. Okay, what are the orbitals? Which orbitals we are generally talking about? n-1d, ns and np. Okay, these metals and also nd. Okay, so these orbitals, okay, these 4 orbitals of the metal can undergo hybridization under the influence of ligands. Means when the ligands approaches to the metal, these orbitals undergo hybridization and form new hybrid orbitals to form bonds with the ligands. Very clear? Metals have their own individual orbitals. When the ligand approaches, these orbitals of the metals undergo hybridization. They come together, undergo hybridization, as a result of which they form hybrid orbitals which are equivalent, and these hybrid orbitals form bonds with the metals. I'll give you an example, it will be more clear. These hybridized orbitals are allowed to overlap with the ligands so that they can form the bonding. Okay, so we have this important table from the I'll say from the NCERT. So if there is a coordination number of 4, then what are the hybridizations possible? You have sp3 hybridization and dsp2 hybridization. Okay, if it is sp3 hybridization, the shape is tetrahedral. With the dsp2, it is square planar. Now if you have 5 coordination number, then you have sp3d hybridization and trigonal pyramidal as the geometry. In coordination number 6, you have 2 types of hybridization, sp3d2 and d2sp3, and these both will give you octahedral. Okay, so I'll just draw the shapes. So for tetrahedral, what is the geometry of tetrahedral? You have metal and you have ligands like this. This is tetrahedral, right? Next, for square planar, you have metal and you have 4 ligands like this. This is square planar. Then you have trigonal bipyramidal. I am writing TBP, trigonal bipyramidal. So you have metal like this and you have ligands like this. Okay, and octahedral we have already done so many times. So metal with octahedral will have 6 shapes or 6 ligands like this. Clear? So now coming to the next one. So here are some examples that we should remember, and directly questions will be asked from these 4 examples only. So CONH3 whole 6 3 plus will have, so you have 6 coordination number is there, so either it is D2sp3 or sp3d2. So for this one you should remember it is D2sp3 hybridization, octahedral geometry, magnetic behavior is diamagnetic. I'll show you how it comes. Next, COF6 3 minus, again 6 coordination number. Here the hybridization is sp3d2 and the shape again is octahedral and the magnetic nature is paramagnetic. Now coming to NiCl4 2 minus, here the coordination number is 4, so either it will be sp3 or dsp2. So you have to remember here it is sp3, and since it is sp3 tetrahedral geometry with paramagnetic nature, and then you have NiCN4 2 minus, here coordination number is 4, the hybridization is dsp2 square planar and diamagnetic. Okay, so now we will be discussing, so what you have to understand is, if it is a strong field ligand, then what happens? Pairing of electrons takes place. Okay, here which are the strong field ligands? You have NH3 is a strong field ligand and C8 is a strong field ligand, so pairing of electron takes place. Now I will explain how the hybridization takes place, how you need to write for one of them. So let's do for CONH3 whole 6. Okay, so yes, okay, so I have for CONH3 whole 6, right? What is the charge of the complex? 3 plus. Okay, so what is the cobalt electronic configuration? 3d7 4s2, right? Cobalt with plus 3 state will be, you will remove 3 electron, it is 3d6. Now if I draw this 3d6, it looks like this: 1 2 3 4. So 1 2 3 4 5 and 6. Now see, ligands are 6 ligands are there, right? So what will happen? 6 ligands will donate electrons to the metal. Okay, 6 ligands will donate electrons to the metal, and in coordinate bond what happens? Both the electrons are donated by the ligand itself. So that is why you need empty orbitals for forming the bonds. You need empty orbitals for forming the bond. So this is 3d and we have 4s, okay, and we have 4p after that. Okay, Now you see, as I told you, NH3 is a strong field ligand. Okay, NH3 is a strong field ligand. So what happens? Pairing of electron takes place. Okay, so what will happen? These electrons will start pairing. NH1, 2, okay, I did one extra here. 3d6, right? 1, 2, 3, 4, 5 and 6. Now what will happen? These electrons will pair up. So how the 3d will look? If they are already pairing up, how the 3d will look? We will have like this. One more box. So 1, 2, 3, 4. So yeah, one more is there. So this is there. Then you have 4s and you have 4p. Okay. Now you see, I have 6 empty orbitals, right? In the 6 empty orbitals, the NH3 can donate its ligand. So what will happen now? See, before that there's one more step. So these 6 empty orbitals will undergo hybridization. They will undergo hybridization to form which orbitals? They will now form 6 new orbitals. So 6 orbitals have undergone hybridization to form 6 new orbitals, that is D2sp3 hybridization. Okay, now these 6 ligands are new hybrid orbitals called as D2sp3 and each of them now form bond with NH3 ligand. You can just write down like this. Okay, so now this NH3 ligands will donate electrons here. Right? NH3 ligands will donate its electrons here. Now once that is done, you can now describe the magnetic nature. So you see in this metal now, is there any unpaired electron? No unpaired electron. No unpaired electron means what it will have? It will have a diamagnetic nature. Okay, and what is its hybridization? Which all orbitals have hybridized? D2, S and P3. So that is D2sp3 hybridization. And since the coordination number is 6, this is an octahedral complex. Getting? So like this, you have to write the complete definition for these all the 4 compounds in the exam. So once one I have discussed, you can try the other 4. Okay, other 3. Now let's move to crystal field theory. It's another way of describing the bonding of metal and ligand. Valence bond theory says that the valence orbitals of the metal undergo hybridization and then they form bond with ligand, right? But here what happens in case of crystal field theory, there is a metal ligand bond to be ionic arising, means the metal and ligand bond is considered ionic in nature, and when ligands approach the d orbitals, they split the d orbitals to reduce the repulsions. So these d orbitals are like this, right? Metals d orbitals, 5 orbitals are like this. When the ligand approaches the metal, it splits into 2 sets. Okay. Now how does it split? That we will discuss. Now splitting of d orbitals depends on the strength of the ligand. If I have a strong field ligand, the splitting will be more. If it is a weak field ligand, the splitting will be less. Okay. So this is the energy of the strength of the ligand. So you can see CO, CN, EN, NH3, these are strong field ligands, whereas I minus, Br minus, SCN minus, Cl minus, these are weak field ligands. So when I have these ligands, there will be more splitting. When there will be these ligands, there will be less splitting. Okay. Now let's move forward to understand the crystal field splitting in terms of coordination number 6. Means when you have a metal, okay, and there are ligands approaching in all these directions. In 6 directions the ligands are approaching. Then what will happen? This d orbitals of the metal, due to repulsion, first its energy increases. Then to reduce the repulsion, what happens? The d orbital splits in 2 sets. One is T2g set and the other one is EG set. In T2g set we have dxy, dyz and dzx, and in EG set we have dz square and dx square minus y square. So these are the splitting in the orbitals that takes place in case of octahedral splitting. Now if you have a configuration also we need to discuss. So let's see, we have for strong field and weak field. Okay, you have this d orbital, 5 d orbitals are present. Okay, now if there is a weak field, the splitting will be like this. Less splitting will be there in case of weak field, whereas in case of strong field there will be more splitting. Right, now what happens if you have D1, if there is 1 electron, So this one electron will go here and there will be one electron going here, right? So what will be the configuration for D1? I'll write here D1, okay, and this is the strong, this is strong filled configuration and this is weak filled configuration. I'll write here, okay. So for both strong filled and weak filled, I will get T2G1 here also, and here also I have T2G1. Now let's talk about D2. When I have D2, so one more electron will come here, and in D2 here also one more electron will come. So for D2 the configuration will be T2G2, and here also for it will be T2G2. Now coming for D3. D3 we have one more here, and so here also I have got D3. So here one more electron will come here. So for D3 I can write T2G3, and here also I can write T2G3. Now it is, till here it was very simple. Now let's talk about D4. Now when D4 is there, okay, in this case there is a possibility that the fourth electron can either go here or can pair up here. Here also the possibility is that it can either go to the upper level or it can pair up here. Now see here the energy gap is very high, okay. The electrons need much more energy to go there, and that much electron providing is very difficult. So the electron tries to pair up here, okay. So in case of strong field ligand, what will be the D4 configuration? T2G4. But here, since the energy gap is less, what does the fourth electron does? It moves here. So what I will get here? This is D1, D2, D3. D4 configuration will be T2G3 EG1. Okay, T2G3 EG1. Now let's move to D5. Okay, D5. Now in D5 also, here you can see that it has to go to a higher energy level. There is no much energy is required, so here it will pair up, and here it can go to the higher level. So what will be the D5 configuration? In case of this one it will be T2G5, and in case of this one it will be T2G3 and EG2. Okay, next we'll talk about D6. Okay, in D6 what happens? The next electron, again here it can pair up, right, 6 electrons, but here you can see all the 5 orbitals are singly occupied. Now if the 6th electron wants to come, it will be less energy here, it will require more energy here, so it will pair up here. So what is the D6 configuration in case of strong field ligands? We have T2G6, and here we will have D6 configuration as T2G4 EG2. Okay, now coming to D7. Okay, if I have D7 configuration now, here the 7th electron has to move here. There is no other option. Already this is occupied. 7th electron moves here, so I will get T2G6 EG1. Here also 7th electron has to pair up here because it doesn't want to go there, higher energy level. So here I will get T2G5 EG2. Right, you can see the difference in configuration. So which configurations are different? D4, D5, D6, D7. Okay, between strong field and weak field ligand. Next comes D8. If I have D8, D8, what will happen? Again one electron will come here, right? So its configuration will become T2G6 EG2. And here also you can see this is all occupied. Here we will have D8 configuration will be T2G6 EG2. Next D9. D9 we have 6 electrons covered here. It will be here like this and here also like this. So D9 will be same for both, that is T2G6 EG3, and D10 will be one more electron will come here and will come here, that is again T2G6 EG4. Right. So the D electron configuration will only vary for this D4 and D7. D4, D5, D6, D7. D8, 9, 10 is same, 1, 2, 3 is same. Okay, please note down this one. Next we'll go to crystal field splitting in case of tetrahedral. So in tetrahedral there is always less splitting as compared to octahedral, and the sequence is different. Here the the 2 orbitals come down and 3 orbitals go up. Dz square and dx square minus y square come down, whereas dxy, yxz and yz goes up. Okay, and here no g is used. Next, talking about the color. So what happens is, you have seen that there's DD splitting, right? So when the light falls on these complexes, these D electrons can undergo DD transition, and these DD transition lies in the visible region, and that is why we find that the compounds of transition elements are colored compounds. Okay, so you can see that when an electron from a lower D orbital is excited to a higher energy D orbital, the energy of excitation corresponds to the frequency of light absorbed. So how much light it absorbs, based on that it goes to the higher D level. This frequency generally lies in the visible region, and the color observed is complementary color of the color that we observe in the molecule is the color complementary to one which it has absorbed. Like for example, there is a trick to remember that I have V, B, G, Y. Okay, let me draw it properly. V, B, G, Y, O and R. Okay, now if the compound is absorbing blue color, it will visible orange. If it is absorbing green, it will visible as red. If it is absorbing Y, it will be visible as violet. So that is complementary colors will be visible. Okay. Next we have something called as last metal carbonyls. Okay, so the homoleptic complex of metal and carbonyl ligands are called as metal carbonyls. There are so many compounds like this, and you should specifically remember Mn2CO10 and CO2CO8 structure. Okay, this structure can be asked. So here they can ask how many CO-CO bonds are there, how many CO-C carbonyl bonds are there. So like this questions can be asked, so you have to remember the structure. Okay, these carbonyl which comes in between two cobalt groups are called as bridging carbonyls. Okay, whereas these are called as terminal. Okay, they are joining two CO groups, so that is why there is bridging carbonyls compound. Now why do we study about them as a separately? Because their bonding is slightly different from other metal to ligand bonds. So what is the difference in that? So generally what happens in all the metal ligand or in all the coordination compounds, ligand forms bond, ligands donate electrons to the metal and forms bond. But in carbonyl ligand, if this ligand is a carbonyl, there is a special bonding apart from this bonding. The special bonding is the metal also donates electrons to the ligand and forms a pi bond here. Okay, so this bonding which metal donates to the ligand is called as back bonding. Okay, so there is a back bonding from metal to ligand which helps in this, which makes the metal ligand bond more stronger. So now we have to understand where it is donating, where it is accepting, which orbitals are involved. Let's see that. So when metal donates, see here, so when carbonyl, this metal ligand donates metal, it donates in the empty d orbital. Okay, empty d orbital of the metal. Now when metal back bonds, okay, when it gives it electrons, it gives electron from the filled d orbital to the empty pi star orbital or empty anti-bonding orbital of the ligand CO. Okay, so let's see here, the metal carbon bond in metal carbonyls possess both S and P character. Okay, means it has both sigma and pi bond. So the MC bond, this bond is a sigma bond formed by the donation of lone pair of electrons on the carbonyl to the vacant d orbital, which is this orbital, vacant d orbital of the metal. Now the MC bond means where the back bonding is formed by the donation of a pair of electrons from the filled d orbital, this is the filled d orbital, to the vacant anti-bonding orbital of the metal. This is the vacant anti-bonding orbital of the metal. Okay, this back bonding is there, which is the reason why these metal carbonyls we are studying separately, and their bond structure is very I can say strong. Okay, now moving to the applications of coordination compounds. So here are different applications, you should be knowing certain important one. So first of all, EDTA is used for the hardness of water, then extraction process of gold and silver. In purification of metal, this nickel tetracarbonyl nickel is used. Then in chloroform we have magnesium, in hemoglobin we have iron, then we have vitamin B12 has cobalt. So these particular things can be asked in MCQs, you should remember that. Next, yeah, so that's all about the uses, and that's all about coordination compounds. So just watch this video, revise your concepts, brush up your concepts, and the next video we are coming on the question practice. Okay, what type of questions will be asked? I'll be taking all the questions of the sample question paper of last year question paper. So all the questions will be included. You will have a good practice. So just revise this concept quickly. Okay, thank you for watching and all the best.